In this video, we will calculate conditional probability. As a reminder, the definition of conditional probability is the probability that event B occurs given that event A has happened. And we represent this by the probability of B given A. So it's kind of like a line that delineates. And the formula for calculating this is the probability of B intersect A, B and A, divided by the probability of A. So in the conditional probability formula, the intersection of the two events is on top, and then you divide by the given probability. You can manipulate, move this formula around by multiplying by the probability of A on both sides, and that will give you the probability of the intersection if our two events are not independent. That means that they actually, when one occurs, the other event changes or it has an effect on that event. So we know that when we have independent events, we simply just get to multiply their probabilities. It's nice and easy, but not so easy when we have events that affect each other. So when we have information that an event A has happened, it actually changes what the probability of B is. Okay, so let's keep these formulas in mind and let's try an example. What's the probability that you draw a card at random from a deck and it's an ace? Then you draw another card at random and it's an ace too. So in notation, I'm going to write this as, we want to know the probability of the first card being an ace and the second card being an ace. And we're going to calculate this given that we know some information. So we're looking to this formula right here. So we want the probability of the first is an ace and the second is an ace. So let's fill in the notation of this formula. So we'll take the probability of that first event, A, or the first card being an ace. So the probability that the first card is an ace. And we're going to multiply that by the probability that the second event is an ace, given that the first card is an ace. So the reason we're using this formula is because this event that the second card is an ace is not independent of this first card being an ace because we are keeping the card. It says you draw it, and the probability that you draw a card from a deck, it's an ace, and then you draw another one. So you're not putting the card back, so there's actually, that probability is actually dependent on what happened the first time. So we can't just multiply the two probabilities together. We have to take into consideration what's already happened, what we already know. Okay, so what is the probability that you draw a card from a deck at random and it's an ace? Well, there's 4 aces out of 52 cards. Okay, what's the probability that you draw the second card at random, it's an ace, given that your first card that you have in your hand is an ace? So the first thing that I realize that changes is how many cards are left, and there's 51, because I already have one. And then I can also think about, well, I already chose an ace, so how many aces are there left to choose from? There's only 3. So now when I multiply these two fractions together and I do a little bit of simplification, I get 1 over 221. That is a very, very small probability that you draw an ace, keep it, draw another ace, very small probability. Let's try one more conditional probability formula problem. So this table below shows the number of survey subjects who have received and not received a speeding ticket in the last year. It also shows the number of their cars, just data that we collected. Now, as you can see here, the bottom is the total and the right side is the total. So we will keep those in mind when we need to use them. Okay, part A says calculate the probability that someone got a speeding ticket given they were driving a red car. So probability of a speeding ticket, just writing it in notation, given a red car. Okay, so using our probability formula, just so that we don't get confused by the table, that means we want what is the probability that someone gets a ticket and drives a red car over the probability of someone having a red car. So from our table, we see that ticket and red car, so speeding ticket and red car is 15 right there. And this is out of, because it's a probability, this total of 665. And then for the probability of red car, we see red car is right here. Everyone that's got a red car goes over to the total of 150 out of 665. So since they're out of the same denominator, those denominators will simplify and we're left with 15 over 150. And that simplifies again to 1 over 10. So the probability that someone got a speeding ticket given they are driving a red car is 1 out of 10. Let's try one more. Calculate the probability that someone drove a red car given they got a speeding ticket. Now you might be thinking we just answered this question, but we didn't. It is actually a different question, so we have to read it carefully. Calculate the probability that someone drove a red car given they got a speeding ticket. So the speeding ticket piece we already know. So I'm going to approach this problem slightly different than I did in part A, so you can see two different ways to do this. Okay, so we know that they got a speeding ticket. That is information we were told. That means that kind of dwindles our pull down a little bit from this big table. So if they got a speeding ticket, we know that they live in this section of the table. And that section of the table has a total of 60 people. So that's my denominator, is the total people who got a speeding ticket. So got a ticket is 60 people. Now of those 60 people, we want to know the probability of a red car. So here's our 60 people. We want to know the probability of red car. That's the 15. So instead of using the formula, I used the table and calculated it that way. 15 over 60, which simplifies to 1/4. Now, even though I say I didn't use the formula, really, that's what I did. I just didn't calculate the probabilities. I just used the numbers in the table. So you can do it like I did in B, or you can do it like I did in A. Both will always work. It kind of just depends on what makes sense in your brain.